So just so everybody is aware, so I'm going to go ahead and start. Just so everybody's aware, right? You can correct page 8 and get points back on that exam. On that exam question. Be sure to check to make sure that your points have been added correctly, right? And if you've got any questions or you think it's something that's right, I'm sorry. Then there's a chance that you might be, entitled to more points than you actually got. Simply because we grade about 100 of these, and we just grade the same question all in a row, and after about 4 hours of that, it just kind of, mistakes can crop up. All right. So today we're going to do another in-class exercise, and this is a really fun one. It's it's a game called the Towers of Hanoi, right? Also called Lucas's Tower. Now this is a pretty straightforward game. The objective is to take this stack of discs and move it from this peg to this peg. Now, of course, if I could just do that, right, it's kind of a boring puzzle, right? So obviously there are rules. Rule number 1, you can only move one disc at a time, right? And to actually make it so that it's a non-trivial puzzle, there's the rule where you move one disc at a time, but for this disc, I can't place it on top of a smaller disc. So I can move this disc over here, but I can't move, and I can take this disc and move it onto here or onto here, but I can't do this, right? I'm putting a bigger disc on top of a smaller disc. So those are the two rules, and the objective is to get this from here, right, all the way over to here, from your start peg to the end peg, right? Okay. Now, just to clarify based on a question I had last night, while the number of pegs may vary from puzzle to puzzle, right? The number of discs may vary from puzzle to puzzle. The number of pegs for this version of Tower of Hanoi that we are solving does not, right? Some other Towers of Hanoi, they do some weird things, like we have 2 stacks of discs and four pegs, but this one, the classic Towers of Hanoi, you've got 3 pegs with as many discs as we want, each one of a different size. Okay. So all right. So obviously starting out with a size 7 puzzle to solve is a bit much, and it does take a lot of steps to solve a size 7 puzzle. So I will go ahead and just start with the classical number of discs, which is to start with 3. Now the objective is to move from here to here, right? From this peg to this peg. Now to do so, right, it's kind of a bit tricky, right? The idea is, okay, so we want to get this bottom peg out. So we want to get this bottom disc out of the way. Out over to here, right? Because if we think about this, what has to happen is that I've got to get these top 2 out of the way so I can move this guy over here, and then I'll figure out how to move these other 2 back on, right? That makes sense, right? So I could do something like, well, if I put this here, well, then I would put this guy here, but now these 2 are in the way, right? I can't move it over here like I wanted to, right? So what I actually have to do is something along the lines of, I've got to move this disc over here to the end, move this guy over here, take this guy and move it out the way. And so now I've successfully moved the top 2 discs off of the 3rd disc, right? And now I'm free to move this guy over here, right? And now I just have to move these 2 discs on top of this peg, on over here, right? That makes sense to everybody? Everybody following so far is just kind of the problem. So I move this out of the way, move this over here, and take this and move this over here. Okay? So, so the idea now, if you're kind of catching on to the idea behind this is actually a recursive puzzle. That was actually a recursive manner in which I just said I wanted to solve this puzzle, right? In order to solve how do I move these 3 discs over from this peg to this peg, right? What did I do? Well, I said, well, the first thing I have to do is move a tower. To move a tower of size 3, I had to move a tower of size 2 out of the way, then move the bottom disc, right? And then move the tower of size 2 back on, right? That was my problem-solving process there. Okay, that makes sense to everybody? That was a recursive process? That was a recursive puzzle? So, okay, so now how do I move a tower of size 2 over to here? Well, that would mean I have to move a tower of size 1 over here, right? Then I'll move that out of the way so I can move the bottom peg. Then I can move this on, and congratulations, I moved a tower of size 2. So now I can move the base out of the way over here to move a tower of size 3. Does that make sense to everybody? Okay, so let's go. So it becomes a bit more obvious to see once we move up to 4. Okay, to move a disk of to move a tower of size 4, right? I have to move this tower of size 3 out of the way, right? I have to take these and move this out over here, same problem, so I can move this bottom disk over to here, right? And then I'll take these 3 and move them over here. That makes sense to everybody? Right? That's the way we solve this. I just take these 3, move them here, then move the bottom disk over, and then move those on. So I've got to figure out how to move this 3 guys over to here, a tower of size 3, which means moving a tower size 2 over here, right? Which means I move a tower of size 1 over here, so there, to there, to there. So now I've moved a tower of size 2 out of the way, so I can move the base of a size 3 tower over there, so I can move this over, and there I've got a tower of size 3 over there. So that means I got to move this bottom disk over here, so I can move a tower of size 3 over here, which means I can move this guy over here. Now I have to move this tower over to here, which means that I need to move this guy over here, so I can take this guy over here and move that. It means move this guy over here, 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 move this guy over here. Oh, missed. So the idea here is that it just recursively, so you basically swap what peg you're on, right? We had a 5th guy, and again, it's the same process. Now, it does take a number of moves. It's specifically, the number of moves this does take is 2 to the nth minus 1, okay? But it's a straightforward algorithm once you get the hang of it. To move this guy, to move your top 4 disks out of the, to move a tower of size 5, I have to move a tower of size 4 over here, right? But to move a tower of size 4 over there, I have to move 3 over there, which means I have to move 2 over here, which means I have to move 1 over here, right? So I can do that, move that out of the way. Move this over here, out of the way. Let's see. And so now I got to move this guy over to here. So that means, and this being color-coded does kind of help, actually. So, and it does get progressively harder as you go up because you have to remember at what layer you're at, right? So I have to move this guy over here. So we take this, so we have to take this guy, move it over here, which means I have to take these 3 disks and move it out of the way over here, which means to move 2 over here, which means to move 1 over here. Right? So I can get this guy out of the way, which means I can do this, this. And now we're back to the puzzle of moving 3 over to this over here, right? So we can move, so that means to move this guy over here, so we can move this guy out of the way. So it's a fairly straightforward algorithm to do. So why don't I go ahead and write that up on the board for us, okay? So I'm going to write some pseudocode onto the board, right? It's fairly straightforward, right? So to solve the towers of Hanoi, we'll define a function called move, and we're going to take in an integer called n, which is basically the number of disks we want to move. Okay. Now, obviously, let's think about how we want to structure how we want to do this in terms of data structures, right? These pegs, right? How am I manipulating them? I'm only putting stuff on the top, and I'm only removing stuff from the top. So, what data structure should I use? Yep, a stack. See, told you. Let's just get in the top of this. Told you stacks are really useful. Okay. So we'll take in a number n, which just says how many of these I'd like to move. All right, so now let's say I take in 3 stacks. First is the source, right? So that's where I'd like to start from, right? I'd like to move n disks from the source to where? I'd like to move from n disks from source to target, and I'll list my 3rd stack as AUX for auxiliary, okay? So I'd like to move n disks from the source peg to the target peg, and we've got this 3rd one over here to use as a temporary holding, right? In regards to that, we'd like to move you know, these 6 over from here to here, these guys have to get moved to the auxiliary peg, so we can move this guy over here, so we can move these other 3, this other stack over here, right? So if you put that in code, that says that if there are disks to move, so if n is greater than 0, right? If n is greater than 0, right? If there are disks to move, I will first move n minus 1 disks from the source stack, right? The top, an n minus 1 tower from the source to the auxiliary stack, right? To that middle stack. And then target is just our 3rd guy hanging out on there. So we've moved so with that, we've moved this tower out of the way, right? Or rather for you guys, we've moved this tower out of the way. Okay? Now that that's moved out of the way, we can do target dot push source dot pop, right? We pop from our starting stack, our starting peg, and push it onto the final destination, right? And then move n minus 1 pegs from the auxiliary stack to the target stack. And our source stack is the 3rd one in that case. All right. So obviously this is pseudocode for the algorithm, but that's it. And obviously a real program that would solve this program would be loads more complicated. And we'll just switch this from push to append. And now it's a working Python program. So that was a lie. It's actually this easy in Java and in Python. It is a ridiculously simple algorithm for solving this problem. It looks like it's complicated, but it's not. Take a look at what it does. It says if there's disks to move, we are going to move n minus 1 of them out of the way using recursively calling this algorithm. We're going to move them out of the way to the auxiliary stack, and then we're going to then we're going to take that last disk, move it to the bottom of our target, and then we're going to take the guys that we moved out of the way and put them onto the target. That's the exact algorithm I was doing, right? When I was doing this over here. Let's go ahead and get this down back to 3 pegs, so I don't have to torture you all with too much. So, right, to move a stack of size 3 over to here, that says the first thing I want to do is move stack size 2 over to here. Okay? So now we're in the recursive call where n is 2. The source is still the same source, but the target is now this middle peg, right? And the auxiliary is here. So to move 2 to here, I need to move a stack of size 1 over to here. And so now we're in the recursive call again, and it says, okay, move a stack of size 0, right? But that's just not going to do anything, right? Then we're going to move this peg over to here. And then it says to move a stack of size 0, but we're not going to do anything there. So we're done with moving a tower of size 1. Now we move. Now that terminates. We're back in the n is equal to 2. We're moving. So we moved the 1 out. We did our n minus 1 call. So we moved this over here. Then we call to move from the auxiliary stack to this stack, right? And now we're back in the 3 call. And now we're back in the n is equal to 3 call, where this is our source and this is our target. We just finished the n minus 1 call, so we move that over there, right? So this is the algorithm that I was using, right? And then we just do that last recursive call to move these 2 disks over to here. All right, so is anybody confused about this so far? Now, I suppose a lot of the confusion, if you are, the confusion is there's no way that works. That looks like magic. That looks way too short to be a solution. It's not. I swear to God, it's not. It's actually a working solution. The only thing that it's not really doing is kind of proving it to you by printing it out. And you can print it out, and you can show the progress by putting a line. let me go and get this in the recording. You can put a line in between here, just right here, that says move, a print line that says move source to target, if you want to just show that is indeed working. Okay, for some reason it decided to lock my computer. Okay, so, right, move source to target. If you just do a print line that says moving from the source peg to target peg, that'll do it. If you give these guys names. But if you're just using the print line statement, it's just going to print out the contents of those. So the other thing you can do is suppose, right, because your source, target, and auxiliary, they're going to change based on what layer you're in, right? What you can do, what I would do is that if you want to print out the status of these guys, is I'd make some static variables. I'd make a static peg A, static peg B, static peg C, so they exist outside, right? And so that way you can print A, then you can print B, and then you can print C. And that will enable you to see the changes go through. Because if you just print source, target, destination, the order of your pegs is going to get mismatched during each call. Although it will still work, right? This algorithm still works no matter how stuff gets printed out. All right. So your objective for today is to essentially code this in Java, which shouldn't be too hard because I've just mentioned that it's fairly straightforward to code. But it looks like it shouldn't be that easy. And the point of this is to say, yes, it looks like a complicated puzzle, but it really is that easy to solve. And full disclosure, I lifted this from the Wikipedia page on Towers of Hanoi, so you might want to go there and use that code for reference, right? This Python code over there that you see on the screen. You might want to use that as reference. All right.